Okay, we're going to practice solving energy balance problems by working on a fairly simple example from the book, example 8.3-5. And so in this example, what we're dealing with is a process in which we have a stream that's a mixture of methane and air that is to be heated from 20 to 300 degrees Celsius. The flow rate of the mixture gas is about 2 times 10 to the 3 liters at STP conditions per minute. And what this problem wants us to identify is the required rate of heat input in units of kilowatts in order to heat this gas mixture from 20 to 300 degrees Celsius. So at this point, what you should do is pause the video and use the information from this problem statement in order to identify a basis and draw a process flow diagram. So from the information in this problem statement, we could draw a process flow diagram that looks like this. The basis in our problem should be the volumetric flow rate that we're given, because it is a flow rate amount. So this is a good item to use as a basis. All right, in our process flow diagram, in our inlet stream, we have our volumetric flow rate, and we have our compositions that are given in the problem statement as well. 10% for the methane and 90% for the air. In the outlet flow stream, we have the new temperature, the 300 degrees Celsius, and really there's nothing in the problem to indicate that the compositions are going to change. So we also have that composition information as well. Now, as far as unknowns in the problem, even though we're given the volumetric flow rate, we know that because we're dealing with a gas, volume is not conserved, right? And so what we should really be looking at is the molar flow rate, right? So we need the molar flow rate for both the inlet and the outlet stream. And of course, the problem is also asking us to identify the amount of heat required in order to heat this gas stream from 20 to 300 degrees Celsius. And so what we need is some sort of heat flow rate. Okay, so those are our unknowns in the problem. All right, at this point, I took the liberty of drawing out our enthalpy table, which is what we're going to use later. We won't fill it in now. We're going to start filling this in when we need to solve for terms in our energy balance. But as you can see, the way I set up this table, I set it up with 5 columns. The first column lists all the different species, and so in this problem we just have the methane and the air. Okay. For this one, it's a fairly simple problem, so we just have two. Everything's in the same phase. Everything's in that gas phase. But if we had, a chemical species that was in different phases, so let's say we were dealing with wet steam, in which we had water in both the vapor and the liquid phase, we would actually make 2 different rows for that, even if they're in the same stream. All right, so we'll get practice with those types of problems later. In any case, for now, we just have 2 columns, one for the methane and one for the air, or 2 rows, I mean. All right, as far as the different columns, so we have one column for the molar flow rate of stuff going into our process, and we have the associated enthalpies of those things going into the process. We also have the molar flow rates of stuff going out of the process, and then also their specific enthalpies as well. Okay, so really this is the sort of format we should be using for the enthalpy table that you're going to fill out. Below, I'm going to put the reference states of each of the different species, right? Because in order to calculate the enthalpies, it needs to be relative to something, all right? So we'll fill out that part later when we start dealing with the energy balance. In any case, we need to see if we have enough information at this point in order to figure out all of the unknowns in our problem statement. And so, what I'm going to do is a degree of freedom analysis, and I'm going to do the molecular version. Okay? Alright, as far as the number of unknowns, the independent species, let me make the format the same. Independent species. And then number of other equations that we should use. Okay? At this point, you should pause the video and you should catalog all of these things in order to see if we have enough information to solve our problem. So if I zoom in here, let's start cataloging all of the items for the degree of freedom analysis. For the number of unknowns, we have three things. We have the molar flow rates, both in and out, and also that heat flow rate. Right? For a number of independent species, we actually only have one. Right? And basically we could either do a material balance on only the methane or the air. Alright? And that's because you'll see their compositions are basically related, right? If you the ratio of the methane to the air is the same in both the inlet and the outlet stream, right? So that ratio doesn't really change. And so if we were to set up a mathematical equation here, we would see that the molar flow rate of the methane just by itself is basically just a fraction of the molar flow rate of the air. And that fraction is the same for both the inlet and the outlet. And so what that means is we only have one independent species. If those fractions changed, right, if there were other streams going in and out of the process, or if there was some sort of reaction going on that would change that composition, then they would be two independent species. But because everything is just the same in the inlet and the outlet stream, that means we only have one independent species. Okay? So that's an important note. It's not that big of a deal for this problem, but it does just tell us that really we only have one unique material balance that we could use. All right. As far as other equations, in order to balance out our degrees of freedom, we need two other things, right? And so those two other things we need, one of them is one that we're always going to have from now on, is that energy balance, right? So that's one equation we could use. The other thing we could use, right, if we're given a volumetric flow rate and we want a molar flow rate, of course what we could use is the ideal gas law. So IG law. Okay? And so in our degrees of freedom, what we have is 3 minus 1 minus 2, which means it's 0. And so we can solve this problem. Okay? All right. Let's now move on to the material balance. And as I said, we only have one independent species. But what we could do, so we can only basically just use one material balance equation. And so the material balance that I'm going to use is actually an overall material balance. Okay? So where I'm actually combining both species together. So I'm going to write out my general form of the material balance equation. We're at steady state. There's no reaction. So that means our inlet is equal to our outlet stream. Right? And therefore, our molar flow rate in is equal to our molar flow rate out. So that's a very simple statement, but this is something we're going to invoke in later on. Okay? All right, and so, we have that the molar flow rates are equal to each other, but what is the molar flow rate? Right? And so we could get the molar flow rate because we know the volumetric flow rate, right? Which is at STP conditions. And so what we could do is we can invoke the ideal gas law, and we could just say that our molar flow rate is just going to be equal to the volumetric flow rate, which we know, which is at STP conditions. And then we could divide that volumetric flow rate by the molar volume of an ideal gas at STP conditions, right? Because that molar volume, regardless of what the gas is, or what the chemical species is, for an ideal gas, the molar volume is always going to be 22.4 liters per mole, right? So that's something that you should have learned in MEB1. In any case, we could start plugging in different values. So our volumetric flow rate at STP conditions is 2 times 10 to the 3 liters per minute. Like I said, the molar volume at STP conditions is 22.4 moles. Therefore, our molar flow rate is 89.3 moles per minute. That's what we get for N1, but for the material balance, we know that is the same value for N2. Okay? Alright, so now we solved for two of our unknowns by using our material balance and the ideal gas law. Okay? Well, now the only unknown we have left is that heat flow rate. Okay? So to get that, we're going to turn to our energy balance. Okay. So we're dealing with an open system. So we're going to write out the energy balance for an open system. Okay. All right, we're not really dealing with any changes in kinetic or potential energy. And there's nothing spinning in the system. No turbine, no impeller. So we don't have to worry about shaft work. So from our energy balance, what we have is that the change in enthalpy of the gas mixture is just going to be equal to that heat flow rate. So very simple statement, and this gives us a pathway for solving for that heat term. Okay? In any case, in order to actually calculate what the heat is, we need to expand out our delta H. All right? So go away. Okay, so delta H here, if we expand it out, it's basically going to be the sum of all these enthalpies going in, which we could write as the molar flow rates times their molar enthalpies of stuff that's coming out of the system. And we could subtract off that same product, but for the stuff going into our system. Alright? And so, from our process, we know that the things going into the system include the methane and the air, and for things going out of the system, it's also just the methane and the air. Alright? So, as far as things we need to calculate, we need to calculate the molar flow rates for air and the methane. Though we could get that because we know what the molar compositions are from our mole fractions. So that's going to be a fairly simple thing to get. That's not too big of an issue. Okay? But what we need to figure out are what are all these molar enthalpy values that we're dealing with. Okay? And so in order to calculate a molar enthalpy, what we need to do is we need to first define some reference states for each of our species. Okay? Alright, and so we'll go species by species. And so at this point, let's consider the methane, species C. Okay? And so before we move on, what I want you to do is I want you to pause the video here, and I want you to think about, what a good reference state for the methane is going to be. Now, for identifying the reference state for methane, you could pick whatever reference state you want, right? And because what we really care about in the end is we just care about the difference between the enthalpies going in and out, right? So as for a particular species, you could pick whatever reference state you want, and in the end, that difference is all that matters. But we could be clever about how we choose our reference state in order to make our calculations much simpler, right? And so what I'll suggest is we actually make the reference state for our methane to be whatever the conditions of the inlet methane are. All right, so if we go back to our process flow diagram, our methane, it's a gas, so that's the phase, and it's coming in at 20 degrees Celsius. And as far as pressure, I don't believe this problem statement said anything about pressure, so we could just assume that's 1 atm. But as we know, when we're dealing with ideal gases, changes in pressure don't even really affect enthalpy, so that part doesn't matter too much. In any case, what we could do is, just to write this out, is we could set our reference state to be 20 degrees Celsius and 1 atm. Right? Okay? And the reason for doing that is because if we set our reference state to just be the inlet conditions, so since reference state for C is the inlet condition, what that means is our molar enthalpy for the methane at that inlet condition is just going to be 0. Right? Because the inlet condition is at our specified reference state. And so in the end, in our energy balance, we'll be able to just cancel out this term because the molar enthalpy is 0. All right? And so that's what I recommend when doing these energy balance problems, which is if you can, you should just set your reference condition to be the inlet condition, your reference state to be that inlet condition. All right? We'll see it won't be the best option all the time. In fact, we'll see that in this problem coming up. But for the methane, it will be. Okay? So I'm going to go back to my table at this point, and I'm just going to write in that my inlet conditions are this. Okay. All right. So for H1C, we already got it. And we don't even need to worry about this term anymore. But for H2C, in fact, let me fill that in here. So this is going to be 0, right? So that's 0 there. And as far as the molar flow rate is going to be, right, we know what the total N1 is. It's 89.3. And we know that the mole fraction of the methane in the inlet stream is just 10% of that. So we could just write in real quick that that's the molar flow rate. All right. And it's the same in the outstream, and the balance is just air. So we could fill in these molar flow rates as well. Okay? But at this point, what we want to figure out now is what's the molar enthalpy, and let me actually make these molars. What's the molar enthalpy of the methane in that outstream? Okay? So to figure that out, we're actually going to turn to the heat capacities. All right? So to get the molar enthalpy of the methane in the outstream, we're going to integrate that constant pressure heat capacity, and we could find the values or the functional form of it for methane gas in table B2. Right? So at this point, let's go to the textbook, and here in table B2, right, it lists all of the or it lists various chemicals, and it lists the functional form of the heat capacity equation, and it lists the constants for that equation. Right? And so if you look at the top here, it says there's form 1 and form 2, right? And the column telling you which equation you should use is right in the middle there. It says form. And so what we need to do is we need to look up methane, which is right here. I'm going to scroll it to the top. All right? And for methane, it's in the gas phase, and it's telling us we're going to use equation 1. All right? So if we scroll back up here, equation 1 goes all the way up to t to the third power. Okay? And then, if we scroll back down, for that equation, we're given 4 different constants, where A is listed as 34.31, and all the constants are listed after that. Okay? And then that last column just tells you the temperature range that the equation is good for. And it's telling us that this equation is going to be good from 0 to 1200 degrees C, which is our problem's well within that range. All right. So we just need to write out our CP equation and then write out the constants. But as a reminder, what I want to remind you is that all of the constants here, in order to get them to fit on the table, they're multiplied by different values. So the A constant's multiplied by 1,000, the B constant's multiplied by 100,000, and so on and so forth. So even though it says, going back to methane, that the value is 34.31, the way it's listed in the table, when we actually use it, we need to divide that 34.31 by 1,000. Right? So just to show you how this is going to work, zoom back in. So from the table, our functional form for the CP of methane is going to be this, T cubed. Where our different constants, where A is not going to be 34.31, but rather it's 0.03431, and B is 5.469 e to the negative 5, C is 0.3661 e to the negative 8, and then D is negative 11 e to the negative 12. Okay? So you got to make sure that your constants are using the right orders of magnitude. Otherwise, your enthalpy values are going to be way off. All right? Okay, so to get H2C, what we need to do is we need to integrate our CP equation from 20 to 300 degrees C. And so if we plug in the CP equation and integrate it, what we're going to get is A times 300 degrees C minus 20 degrees C. We're going to get B divided by 2. And then the way the integral works, it's 300 degrees C squared minus 20 degrees C squared. So this difference, the whole thing isn't squared, right? But it's each individual temperature is squared, right? So make sure you're doing your integration correctly there. Okay. All right. I'm going to go to the next line since this gets a bit complicated. So now we have C divided by 3. That's 300 degrees C cubed minus 20 degrees C cubed. And then plus D divided by 4. We have 300 degrees C to the 4th, 20 degrees C to the 4th as well. Okay? Alright, so at this point, got to plug in the A, B, C, and D. And then if we calculate this, what we get is a molar enthalpy of 12.07 kilojoules per mole. Okay? Alright, so now that we have that value, we'll go back to our table and we'll fill it in. Alright, so now we got all the enthalpy values for methane. So now what we got to do is air. We could take the same approach with air, and then you would get, that's fine, you could do that and you would get the correct answer. But fortunately, in the book, there's actually a quicker way to do it. All right? And so rather than calculating the specific enthalpies from, or the molar enthalpies from the heat capacity values for air, which we're given, we could do, what we could instead do is we could go to a different table in the book. We could instead go to table B8, which just lists the specific enthalpies for different sorts of gases. It's a small collection, but fortunately for us, one of the gases in this table is air, right? So what we could do instead is we could actually just look up values for the specific enthalpy for air, right? But of course, if we use this table, that means we need to we need to use the reference state of this table. Unfortunately, this table gives us that reference state right in the top row there. Right? The reference state is our gases, pressure 1 atm, and temperature 25 degrees C. Okay. All right, and so to use this state, so for air, I'll write it out. For species A, I'll say, the reference state is a gas, 25 degrees C, and 1 atm to match table B8. Okay? And so if we do that, we could mostly just look up the air values. For the inlet air, right, it's at 20 degrees C, which isn't directly listed on the table, so you would have to interpolate. I'm just going to write out what that interpolated value is. But the outlet air is at 300 degrees C, so that molar enthalpy is just listed there. Okay, and so we could go back to our table. We could write out the reference state for air. It's going to be G, 25 degrees C, 1 atm, and plug in the values here. 8.17. Right, and so what I want to emphasize here is that the different species in the problem do not need to have the same reference state. Right? They can have different reference states. You just need to be consistent when you compare the species from their inlet and their outlet streams. Okay? All right, and so we filled out our table. And so why is this useful? Okay? Well, if we go back to our expansion of the molar of the enthalpy term, right? The way we wrote it, we basically just have molar flow rates times their enthalpies, and then minus the inlet ones as well. Well, the way we set up the table, what we have are molar flow rates times their enthalpies. And so in order to calculate delta H, all we need to do is just go back to this table and just find all the values that are next to each other and then subtract them off. And so this table makes it really easy to visualize all the numbers that go into your delta H dot calculation. All right. So delta H dot, we just need to go through the column, or through the table. So what we have is the outlet methane flow rate times its molar enthalpy plus the molar flow rate of the outlet air times its molar enthalpy minus, even though I said we'll cancel that out, I just want to write it for completion's sake. This, the methane inlet times its specific enthalpy, which, because we're at the reference state's at the inlet conditions, it's 0, and then the conditions for the inlet air as well, which is 80.4 times negative 0.15 kilojoules per mole. Okay? So in the end, what we get is 776 kilojoules per minute. But we need to convert this into kilowatts, so we need to convert minutes to seconds, and 1 kilowatt is 1 kilojoule per second. So our final answer is, in order to heat this gas from 20 degrees to 300 degrees, we need to add 12.93 kilowatts of heat. All right. And so with this problem, there's a lot of information that we need to keep track of. But by developing this enthalpy table, it gives us a nice and clean way to keep track of all our enthalpy values.